All right. So this is CIS 256. This week, we're going to talk about algorithm analysis. Also, you may heard about big O notation, which is related to this topic. So what is algorithm? Hold on. A algorithm is a sequence of steps to solving a problem. For example, in week 1, we already discussed a lot of algorithms in your discussion. And here is a algorithm to make a lemonade. That's an example. All right. So whenever we talk about algorithms, we need to talk about the efficiency of that algorithms. Okay. So computers, as you know, are getting faster and faster these days. Thanks for Moore's law, we get the smaller chips but have powerful performance. So maybe one day the performance hardware is so fast that the algorithms not the efficiency of algorithms not matter. However, we are dealing with a lot of data sets, especially these days. We heard about big data, and oftentimes you are dealing with, a Google of numbers. So it's really, really big, right? So, and a simple solution may not scale with size in a acceptable manner if you have a bad algorithms. So it's very important to make sure that you know how fast your, how efficient your algorithms are with the input size growth, okay? But how can we decide which option for our programs or which algorithms is efficient? You probably have a lot of different ways to solve a problem, but which one is more efficient, right? And in particular, we care about time and space efficiency of the problem. In other words, how much memory the program will occupy and how fast it will run. And oftentimes it's a trade-off, right? We sometimes to save time for memory, I'll save memory for time. So let's talk about time efficiency for now. As you know, a program can be implemented in many different ways. You can solve a problem using different algorithms. We like to separate the choice of implementation from choice of more abstract algorithms. Okay, for example, if you want to compute a sum of natural numbers 1 plus 2 plus 3 all the way to n. All right, calculate the sum of first n natural numbers. There's different ways of doing it. The first algorithm is basically you iterate through a range from 1 to n plus 1. In Python, n plus 1 is not included, just so you know. And then you just add them one by one and return the answer. Okay, so how many steps will this algorithm use? If you look at the for loop, okay, it will iterate this total sum n number of times, and with n become bigger, you have your steps takes longer too if each step takes a fixed number of time. So we typically call this O of n algorithm here, right? So because this total time is a function of input data size n. Now on the right hand side, if you do some mathematical calculation, you'll find out that there is a formula actually to compute this. Basically, it's 1 plus n, 2 plus n minus 1, 3 plus n minus 2, and so on, and they are all equal. So you just you just multiply them with n number and divide by 2 items. That's the formula for the sum of the first natural numbers. How efficient is this? Well, it only takes one calculation, one step. So no matter how big the n is, you always compute this one step. So this is O of 1. So it's constant time, right? So obviously these two have a huge difference in terms of how long it takes. Clear winner is the second one. Okay. How to evaluate efficiency of programs? You can use a timer, run the two programs in the same computer, and see who finish early, or you can count the number of operations in your program. But we still need a more abstract notation for order of growth, which is independent of what computer you're using or how you implement these algorithms. So first of all, there is some mechanism that you can time a program in Python. You just need the time module, right? So one way of doing it, obviously, is you insert these two statements before you want to calculate the critical path where this algorithm runs. You can insert start time dot time, and it will give you the system time in seconds. And once you're done, you just stop time. You just call it again. You'll get two different numbers, and if you subtract them, you get the number of seconds in between. All right, so that's one way of doing it. But timing programs is not the best way to evaluate different algorithms, because, for example, the steps or running time varies between algorithms. All right, that can be measured by this timing program. That's no problem, right? Because different algorithms have different running time. You can use that to differentiate it. But how about different implementations, right? That will affect the algorithms. Okay, if you implement in Python versus Java, a different language will have a different running time. Of course, Python runs slowly, but that's not a way to compare algorithms, right? And of course, it varies between computers. And also, if your input size is small, the variation is big. It's not predictable. So in all, this is not a good way to measure the efficiency, because there's too many external variables. So okay, back to drawing board. What else we can do? Well, somebody may argue we can count, instead of count actual time for the running program, we can count how many operations, right, for each steps in the software. The operation includes mathematical operations, comparison, assignment operations, and generally accessing object memory, like accessing data in an array, etc. And if you count the number of operations, we may be able to compare algorithms, because let's assume each operation takes fixed amount of time. That's, for example, here, the first assignment is one operation. The for loop, this condition is one operation, and then there's plus equal to I is one operation, right? So, sorry, two operations. So you have to access the memory and add one to it and return to that memory. And then total is 1 plus 3n, because the for loop takes n, round. So it's 3 times n. For each round is 3 operators. Will that be good? Well, it's if you compare operations, its count depends on algorithm, of course. It can compare algorithms. It's independent of computers, because it's now hypothetical running in your head instead of for computers. But it also still depends on implementations, right? Yeah. So, and it's not a real definition of which operation to count. That's another problem. So we want to actually consider different inputs. We can come up with a relation between inputs and the count. So now we need a better way. There's going to be a better way. So in other words, timing and counting evaluate the implementation of the algorithm, does not be the algorithm itself, right? We want to, the timing also evaluates the machine. Different machine has different timing. We want to evaluate algorithms and scalability, meaning the running time as a function of input size. So there's going to be a better way. What's that better way? Okay, by the way, so let's talk about the input, right? Because this is a functional input. What could be an input? Well, the input could be a integer, like my sum. You add a number, a single integer. It could be the length of the list, and you may even have a multiple parameter function. Then you want to decide what the input means. Okay. And depends on how you define the input, it may change how program runs. For example, if you define a search function with a list and element, right? So if the element is the first element in the list, that's your best case. Okay. And then if it's on the list, end of the list, it's worst case. Average speaking, it's in the middle of somewhere. So it's average case. About half of the elements you have to go through before you find the element E. So we still want to measure the behavior in general way. All right. Suppose you're given a list of some length L. Now, the best case, which defines as a minimum running time over all possible inputs of a size N. So it's constant for such element because it's first in any list. The average case is the average of all the possible inputs of given size. That's for practical measure. The worst case is the maximum running time over all possible inputs of given size, right? That's actually the big O notation is after, it's the worst case scenario. Say in search element is linear because the worst case, you can look for every single element in the list if you find the target. Okay, so order of growth. Our goal is to evaluate program efficiency when input is very big. All right, think big. As input size grows, how the program running time grows, and we need to have upper bound or worst case scenario on the growth. We don't need to be very precise, like one or two operation of it's not a big deal. We just need to like comparing the order, right? Not exact growth. So 3n and 2n is not that big deal. We will look at the largest factors, which is the critical section of program will take the longest to run. Okay. So here comes the big O notation. O means omega. Big O notation measures the upper bound on the asymptotic growth, often called order of growth. So that's big O. We oftentimes write as O of a parenthesis, right? And in the parentheses, there will be different numbers to represent different order of growth. And remember, that's to measure worst case scenarios. And it expresses the rate of growth of program related to the input size. And we're we're evaluating the algorithm itself, not the machine or implementation. Here is some typical order of growth graph. The x-axis is input size and y is the basically operations or whatever. So there is exponential growth, cubic, quadratic, log linear, and logarithmic. So there's some different order of growth. So here's some notation. O of 1 is called constant running time. It could be 100 steps or 1,000 steps, but if it's fixed, it's not a function of input size, we call it constant. Log n is a logarithmic running time. You can think about something like binary search is of log n, because every time you search, you throw a half data away. On is linear running time. Of course, it's obvious, right? On. So it grows linearly with your input size. And log n is log linear, typically as when you sort array in order, that's log and log n. And the power of c is polynomial running time. C is a constant. And c to the n is called exponential. All right. So the exact step is O of x, right? We are not looking for the exact steps, but it's just roughly order of growth, so the order, right? Here, example here, you have a function that calculate the factor of number n, a factorial of number n. So how many number of steps? in the while loop, right? You have 1, 2, 3, 4, and 5, including this and greater to 1 step. That's 5 steps in the while loop, and you have to go to n times. So it's 5n plus the assignment operator, answer equal to 1. That's 1 step constant, and return is 1 step. So it's 1 plus 5n plus 1. Worst case is O of n. We can delete or omit the constant term because the leading term is the n here. And we can also throw away the constant term before the n. So it's instead of say O of 5n, we're just interested in n. So O of n is still linear. 5n, 7n, 2n is always linear. So we ignore the additive terms, constants. We also ignore the multiplicative constants. That's where the big O notation comes from. All right, so here's example. If O of, and it can be written as n squared plus 2n plus 2. We ignore the lower order terms. We only have n squared left. So that's the second one. And the third one, because n grows faster than log n, so this is overall ON logarithm. And same as here, n log n is faster than linear, so it's n log n, but we also ignore the constant multiplication factor. This one, 2 to the n to the 8th power, that's a constant polynomial, but 3 power of n is exponential, it's more faster, so 3n it wins. So that's why overall this is O of 3 power n. Okay. There is some additional law for optical notation. If the two functions, f of n and g of n, is independent of each other, right? They're sequential. Then the overall big O notation is the sum of these individual operations. For example, you have two for loops in sequential. You have to do 1 for loop after that, the second for loop. So the O of order of growth is O of n for the first one, and O of n squared, n times n for the second one. Overall, it's O of n squared plus n, and it's on n squared because the dominant term is n squared. Okay, so that's the additive rule. There is a multiplication rule. If this nested for loop, then its multiplication is O of fn times gn. So here, the outer loop has n, O of n. Linear is also O of n. So overall is n times n in squares. Okay, so that's multiplication. Okay, here example, anagram. Anagram is basically a string or a number that you can read backwards and forward. They're the same. So here is a string of anagram detector. Here, the implementation is have 2 for loops. The outer loop will go through each character of string 1, and the second loop is also goes through each character of string 2. If the C1 and C2 are equal, then mark C2 in S2. And if all S2 are marked, I'm sorry, the anagram is not what we call it. It's not palindrome number. Sorry, I thought it's palindrome. Anagram is basically, the string has all combinations. I mean, all the characters in the string can be rearranged, and they use the same number of strings, right? But it's different word. So we just count one by one, and if every string in C2 can be found in C1, they are anagrams. So, but the question is, what is big O for that? You can see there is 2 for loops, right? And so if each size, like number of, is defined as number of characters in the string, n, then you have to go through n and n multiple together, so n squared, right? The other way to define anagram is we sort the anagram first, and then we compare each one. When you sort it, the order of growth is n log n, as we saw, whether you merge sort or quick sort. When you compare, it's going to once, so it's O of n. Overall, because you're doing two steps not parallel, sequentially, you add them together, and n log n is a dominant factor. So it end up with O n of log n. So it depends on your algorithms, your complexity changes. So we reduce the n squared algorithm to n log n. Can we do better? Probably. So the brute force way, compare all combination S1 and search for S2 is really slow. This is a bad case, like dog versus God, right? You know these are anagram by just looking at them. But in computer, you want to list all the combination of DOG. Okay, well, what is the order of growth for that? Well, so if you look at the position, there's three positions. In the first position, and you have three characters to select from. So the first position is free. Nobody have selected anything yet. So you have three different letters to select from. Once you are fixed with one letter, the second position, you only have two letters left. And once you fix the first one and second one, the third one, you only have one position left. So it's 3 times 2 times 1, which is 3 factorial. So this algorithm is of n factorial, which is really big, very bad. Don't do that. Number 4, we can do something about a counter. A counter is a Python library or object that can easily count number of characters in a string. If you say counter of apple, it will give you this dictionary like construct where it give you the key of dictionary is each letter, and the value is the number of occurrence of that letter in this. So hypothetically, anagram, it means if you take a counter of that string, two strings, if their counter is identical because it's anagram, right? So you have the exact same number of frequency of the character occurs in each word, then they are anagram. So you can do the counter and you compare their equal. That's it. Very, very interesting. So what's the O of that one? Well, the comparison will take a constant time. However, the counter itself will do some, probably I would think it will go through each letter and tally them. So it's about O of n, right? And do some calculation. So overall, this one is like O of n. It's still better than previous O log n and n square. Not to mention the exponential one and factorial is really worse, right? So it depends on how you implement this, the algorithm. There's significant saving in time, especially when you're dealing with a big number input, right? So here is some category. Here we already know the sum of all integers. If you use the formula, it's gonna be O of 1, which is constant complexity. Log n, binary search, like I said, if you have a sorted array already and you just doing binary search, you will find a number. All you know if the number is not in the list in O of log n. Okay, so now here's another example. It's a little bit ambiguous because the input I is a integer you want to convert as string, and here you just go through each digits by modular 10 and append to the result, right? So and then return it. So it depends on the number of digits of that integer, not the integer itself. Okay. So this is of O of log I, because how many times I can divide I by 10? This is the This is the thing, right? It only runs how many times you can divide by 10, and it's about log 10 of I. All right, so the whole thing takes log 10 of I, and these are constant. So overall, this algorithm is log of I. Now, and here is factorial. Like I said, if you do the calculation, it's only it's a for loop with n numbers, and you multiply together. That's of n. And if you implement this factorial in recursive manner, it's still of n because you have n number of stacks calls. Merge sort, it's log linear complexity. We'll talk about sorting algorithm later, but again, this is n log n. And then polynomial, for example, quadratic is the most common one. So that means the complexity grows with square of size of input, right? N squared, okay. If we have nested loops or recursive function call, for example, subset of if every element in L1 can be found in L2, then they're subset. So you have two nested for loops. Although you have an early break, but it's still overall, it's O of length of L1 times length of L2. Because worst case, remember, when L1, L2 the same length, none of elements of L1 in L2. That's n squared. All right, polynomial. So, and finally, exponential, which is pretty bad complexity. You want to avoid those exponential one, right? Like Fibonacci numbers, tau, Hanoi, those are exponential. That's why it's a famous problem, which takes a long time to solve the puzzle. Very many important problems are exponential, unfortunately. So we need a more clever way of solving those things, and such. Okay. The famous exponential algorithm is you list all the subsets of the list, right? Including zero empty sets and the sets that including everybody. So so basically this algorithm is basically a recursive function where you solve a base case and then extension of the list on top of the base case, right? So you solve a smaller case when you have excluded everything but the last one. And you append that to the list and repeat for the rest of them. Once you're done, you get all the subsets. So this is of 2 to the power of n. So one caveat of determining a big O of notation is how you define the size of input links. What's the meaning? In this function, okay, you're converting that integer to a string. And you are doing this for loop with a answer appended with each digit converted to integer. You essentially it's the length of s, right? So it's log n. N is length of s. But not integer n, not integer n. Okay. So next is a Fibonacci number. We could also so in this non-recursive calls, we are basically only calculating the last two terms, and the third term is sum of last two terms. And you just repeat that. It's the best case is the first one, the constant. Worst case, you have to go through all n numbers, so it's O of n. But recursive is worse because you have to recalculate everything that you calculate again is 2 to the power of n. So summary, we use big O to compare the efficiency of algorithms that's independent of the computer you use and the number of steps you implement. And big O notation is using asymptotic notation, and we consider an upper bound of that case. It's basically a worst case analysis. Here is the complexity of most common list functions. All right, so we'll have some quizzes for you for this chapter. Read the chapter 2 as well. Good luck. Bye.